All right, so we are starting Unit 8, which is DC circuits. So we're talking primarily about electric current and voltage sources. What is resistance? Kind of Ohm's Law. Within current, what's the difference between direct current and alternating current? We'll talk about electric power and then the different types of electric circuits that we can form with resistance elements. So we got to first understand what the flow of charge means. Make an analogy with water. If we had an area of high pressure with water or any fluid, that water would want to go from that area of high pressure to that area of low pressure. Okay, it's the same thing with electric potentials. So if I have an area of high voltage, high electric potential, it will flow to the area of low electric potential. So the electrons will go from like the high potential to the low potential, so like the positive terminal to the negative terminal on a battery. So what electric current is, it's the flow of those charged particles. So basically, how quickly are those electrons flowing? So we talked about, just Q, charges or electrons, the amount of electrons we have before. So how much charge we have, and how quickly it wants to flow. So in metal wires, conduction electrons are the charge carriers, or those free electrons that kind of be passed along in the material, and our protons are bound with a nucleus, so the protons don't move. It's just those electrons are kind of moving along. The rate at which electric flow is measured in is 1 amp being 1 coulomb per second. So charge per second, charge per time, that's the rate. And the current is actually flowing through the circuit. Okay? But you have to have a voltage established across the circuit. So we have to have something that's pushing that flow. So which of these statements will be true? Electric current is the flow of electric charge. Electric current is stored in batteries. Both A and B are true, or neither A nor B are true. And the correct answer is A. So electric current is a flow of electric charge. So it's the electric charges flowing with time. So now a voltage source. We have to have something that provides that electric potential difference, something that causes us to have an area of high potential and an area of low potential for the charge to want to flow between. Okay. So we have some conductor, one end's at the high end of the potential, one end's at the low end of the potential. So it could be different sides of the battery, the high potential side, the low potential side, so the positive and negative. It could be a generator. So in class we demonstrated that Can-Crank generator. So we have things like that inside of power plants. There's generators that are spinning around causing areas of high potential and areas of low potential. So for electric potential difference in a chemical battery, which is what most people are used to dealing with, we actually have some chemical reaction occurring, so the disintegration of the zinc or lead in acid that causes those electrons to be want to pushed along by the electric potential difference that forms. So the actual energy stored in a battery is a chemical potential that then becomes an electric potential as those bonds break down. So now, to actually flow, they have to flow through something, well, through a wire, through a different element. So in this picture here, we have something called resistors. All right. So this first one here, this is something called a variable resistor. You're probably used to seeing variable resistors in things like knobs. So like, think of a radio knob, like a volume knob. That could be a variable resistor. All right. These ones here are more traditional resistors. Okay. This one down here, that's another variable resistor. This one over here, that one's kind of cool because that's a photoresistor. So that's a light-sensitive resistor. So depending if there's light on it or not, the resistance value changes. Now, one thing I want to note, if we look at these ones right here, you'll notice there's little color bands on there, right? So one looks like it's like red, red, brown, gold. One looks like it's like blue, green, yellow, gold. And there's like a yellow, red, red, gold. Just looking at the different colors going across from right to left there. And we can actually use those colors that are banded on there to figure out what value resistor those should be. All right. Some of the ones more like this would normally have something written right here saying what they are. But these ones with the color bands, you actually have to decode them. We'll actually do a lab where that'll be part of the lab, but we have to decode what those resistors are. And the whole point of a resistor is that it regulates how much current can flow. So think of like with water, you have a valve, like a knob on your faucet. You can open it up so a lot of flow comes out, or you can close it up so only a little flow comes out. And that's what the resistor does. It's restricting how much flow can go through a circuit. So now, the factors that cause electrical resistance are things like the cross-sectional area. So the resistance is inversely proportional to the cross-sectional area. So the smaller the area, so if I have a very small wire, so something like this versus something like this will be high resistance, this will be low resistance, all right? So thin wires have more resistance than thick wires. So when you buy cheap electronics sometimes, like I don't know if any of you ever bought a cheap USB wire or a charging wire for like your iPhone, and you'll notice they sometimes break or burn out. Well, that's because they're made with thinner wire. It's cheaper, but it also can't handle the higher current values that are needed, and they can burn out or break because of that higher resistance, that higher amount of heat they generate. The other thing is they're directly proportional to length, and this kind of makes sense. So if I had to go this distance versus if I had to go this distance, right, the longer one should have more resistance in it, right? Just like if you're going to walk down a short haul versus a long haul, there's more resistance going down the longer haul. Material can affect it. So rubber doesn't conduct well. There's going to be a lot of resistance there. Copper will conduct a lot better. Then there's temperature. So certain values of resistance can change with temperature. So some materials, that's actually beneficial for us that it changes with temperature. We can use that as a way to run like a thermometer. So if you ever heard of like a digital thermometer, that works with something called a thermistor. It's a temperature-dependent resistor, thermistor, because of that principle. So there are things called superconductors, and these are materials that almost have no electrical resistance, and they don't generate heat. There's something that also called a high-temperature superconductor, which means it can carry a lot of current at a fairly low voltage, but it works at more like a room temperature value. So most superconductors are at very, very cold temperatures, but a high-temperature superconductor is more like room temperature. We're not talking like very, very high heat. We're just talking it's more like room temperature. So now if we take these three concepts, current, voltage, and resistance, we can combine them. And that's what Ohm did. So George Ohm came up with something known as Ohm's Law. And it's the relationship between voltage, current, and resistance. And basically what he found out was that the current in a circuit varies in direct proportion to the potential difference, which is the voltage. And it was inverse with the resistance, okay? So I would equal V over R. So for a constant resistance, so if R stays the same, if I was to double the current, I would end up doubling the voltage, all right? Now on the other note, if I double the resistance and doubled the voltage, so if both V went up by 2 and R went up by 2, I'd have the exact same current, all right? So again, to remind you, resistors are that circuit element that regulates the current inside the electrical device that you've built, or electrical circuit that you've built. So we'll check in here. If I was to double the voltage in a simple electric circuit, what else would double? Would the current double, the resistance, both A and B, or neither A nor B? And it's the current. Because again, if we think of this, I is equal to V over R. So if this goes up by a factor of 2, this would also go up by a factor of 2. Okay, and that's assuming that the resistance didn't change. So electric shock. So a lot of people wonder why, again, we dealt with like the Van de Graaff generator and we didn't get hurt. But if I was to like, accidentally somehow stick a electrical thing into the outlet in the wall, I could get kind of injured or killed from it. Well, that high voltage that the Van de Graaff generated was at a very, very low current. There was not a lot of electrons flowing, all right? Whereas the wall outlet can generate about 20 to 40 amps of current, a lot of current, a lot of charge. So it's actually the current that damages and can kill you. So your body, depending on what parts of your body is, what, skin, muscle, fluids, bone, your resistances range from about 100 ohms to 50,000 ohms. So charges don't naturally want to just flow through you easily. I mean, we are electric because of our nervous systems. That's why, muscle tissue and nerves are those lower resistances on there, but like your skin doesn't want to have conduction go through it. So that's part of it. Now, one of the other famous things people always think of is, well, how could squirrels and birds sit on wires? Well, that's because if we think about it, they're at the same electric potential, the same voltage. So both of his feet here, all right, if I look here and here, they're both at, let's say, I don't know, 240 volts, right? So if there's no change in electric potential, there's no current that can flow through him. The current would just rather keep on going through the wire, not through the bird. But if now all of a sudden that poor bird was to step on the actual pole and then still have one claw on the wire, well, then he's got a path to the ground because the pole's probably the lower electrical potential, and zap, he could get an electrical shock. So now we have DC current versus AC. So like I said, there's different types of sources for our voltage. And reason for that could be how it's being generated for the current. So direct current means that the flow of the current is only in one direction. So that's like saying the electrons flow from the negative terminal towards the positive terminal on a battery. And you're like, well, wait a minute, why do they flow that way? Did you say high potential, low potential? Well, if we think about it, the charge of an electron is opposite how we define the field. So the electron actually flows opposite the current. The electron actually flows from negative to positive. It doesn't flow with the current, it flows opposite the current. And that's a battery. It just flows from one direction to the other. The alternating current, that's like your outlets, all right? And they go back and forth and back and forth and back and forth. And you're probably like, well, why would you do one versus the other? Well, the reason you do AC is it's more efficient because the electron in the wire doesn't have to make the full round trip. So imagine an electron having to leave the power plant, go all the way to your home, go through like your light bulb, go back through another wire, back to the power plant. That's a pretty long trip. Lots of wire it had to go through, so lots of resistance. Not the most efficient, lots of losses. Whereas if we're dealing with alternating current, that electron goes forward a little bit, comes backwards a little bit, goes forward a little bit, comes backwards a little bit, just flipping direction constantly. And this was the big battle that happened between Edison and Westinghouse, okay, aka Tesla. All right, Tesla was a big fan of AC. He went to go work for Westinghouse. All right, Edison liked DC. All right, most all the original electrical equipment was Edison DC equipment. Unfortunately, as this war went on between the two of them, Edison lost this one. He lost this battle to Westinghouse and Tesla. There's lots of bad blood that you can read about on these two, and lots of very odd things that come out of this battle of PR on which was better, DC versus AC. Now that also gets us in this idea of electric power. So electric power is the rate at which electrical energy can kind of basically be converted from one form to another, to do some work. So because power normally we think of as work over time, but now we're going to think of this instead as power is current times voltage. Because if I do all kinds of fancy math, I end up with P equals IV. And power would be in watts. So the other thing we have to remember still is V equals IR, or I equals, the whole V over R piece, right? This is Ohm's Law, right? So this was Ohms. And if I've got, again, P equals IV, I can at times combine these two equations. So what if I don't know the current? Well, maybe I can substitute in voltage and resistance to the equation. Or what if I don't know the voltage? I can substitute in current and resistance instead, all right? So these can be both substituted into this equation to make two other variations of the equation. And it will still give you an answer in watts, how much power we're using, all right? Now, this makes us think about what we actually use in our home, because items like computers or televisions and whatnot will have a power rating in watts, or light bulbs have a power rating in watts, how much current times voltage they're using. But if you go and look at your actual electric bill, on the bill, it'll say something like kilowatt hours. So this is how many 1,000 watts that you used every hour, all right? And that's what they bill. It's normally 10 cents to 20 cents for every 1,000 watts per hour that you use. But then when you realize how many hours there are in a month and how much stuff you use, that 10 cents per kilowatt hour becomes hundreds and hundreds of dollars, right? The average home uses about $200 worth of power every month. But if we look at this though, that's power times time. Power times time is actually energy. So you're actually buying energy, not power, from the electric company. Let's look at an actual electric circuit. We actually have to have a closed path to have an electric circuit. So an example here could be have some sort of pump, which is like our voltage source, a valve, which is like our switch, turning things on and off, and then we have a line, right? I know I talked before about a valve could be like the resistor too if we had a variable resistor, but we'll use the valve as a switch. And then the line that's got some odd resistance to it. So again, you've got some flow of electrons, which are opposite the direction of current, and we have to complete that circuit. So a little better diagram of this is we could have something called an open circuit or closed circuit. So if you look up here, if my switch is open, the circuit is not complete. There's no way for the current to flow. There's no way for the electrons to flow. But if I close the switch, my electrons can leave the negative side, my electrons flow out, go through the resistor, or the light bulb, or whatever the element is that has resistance, and make it back to the positive side, all right? But that would mean that my current actually flows the opposite way, because remember, current is going to flow from positive to negative the way it's been defined because of electric fields and things like that. And the electrons go from negative to positive because, again, an electron moves opposite an electric field. Electric circuits. So electric circuits are, normally connected in multiple ways. It's not normally one thing in the circuit. So you might have multiple bulbs or multiple resistors or whatever. Sometimes they're connected in series, which means there's a single pathway that the electrons can flow through, or they could be connected in parallel. Parallel means there's multiple branches, like parallel lanes on a road, right? I could be in one lane or the other lane, and they could flow that way. Now, there's benefits to each, right? In one case, the current through each in a series is always the same, whereas when in parallel, the voltage across each is always the same. For cheap Christmas lights, you normally have cheap Christmas lights are wired in series. The really expensive ones are wired in parallel. Why? Well, if a series system happens to have one bulb go out, they all go out. If they're in parallel, one goes out, the rest of them stay on except for the one that went out. So that's the benefit for the ones that are in parallel. If we look at this, though, that means we can add resistors. So if they're in series, resistor 1, resistor 2, resistor 3, the resistors just add together. So if this was like 10, 20, 30, 30 plus 20 plus 10, that would be 60 ohms total. So instead of having these three resistors, I could have just used one 60 ohm resistor. That's the equivalent resistance. All right, not too hard to understand, nice and easy. So again, the electrical current has a single pathway. Total resistance is just the sum of the individual. The total current is equal to the voltage supplied by the source divided by total resistance of the circuit. Then the total voltage that's across the circuit is divided into little voltage drops. So basically, if I have 10 volts coming out of the battery, every time I go through an element, I lose some of those volts. So I go like 10 minus, then like 2, then like minus 4, then like minus, whatever's left, right? And it just keeps dropping each time we go through. And the voltage drops will drop proportional to the resistance. It's the same current through whatever resistor we happen to have. But again, if one fails, they all fail. Now, if they're in parallel, what happens here is we get this thing called a node that forms right here, and the currents break up. So the total current leaves the battery. It breaks up across the three resistors because from here to here, they have the same voltage or same electrical potential across all the resistors. But now adding the resistors is a little different. When they're in parallel, we have to add the inverses. So it's like adding the inverse of, again, if we go back to that whole 10, 20, and 30 thing, right? It's like adding 1 over 10 plus 1 over 20 plus 1 over 30, right? So to add those fractions, I'd have to find a common denominator. Well, 10, 20, and 30, it's 60, so I'd have like 6 over 60. I'd have 3 over 60, and then I'd have 2 over 60, right? So 3 plus 2 is 5, plus 6 is 11. So here I'd have 11 over 60 right now is equal to 1 over the R equivalent. So I divide that out, and then I'd have to do the inverse to get my actual resistance, all right? Not quite as easy as it is to just add them 1, 2, 3 for series. There's a little more math involved here, right? So if I do this out, 11 over 60, that gives me like a 0.1833, right? Right now equal to 1 over R, E. So that means once I flip it, Re, in this case, would become 5.45 ohms, which is interesting because it's less than any of the individuals. So as I add things in parallel, the total resistance actually lowers for the system. All right, so at 10 and 20 and 30, I'd be left with a 5.45 ohm resistance for the whole system. For parallel circuits, the voltage is the same across each device. All right. The total current in the circuit divides among the parallel branches, so basically the current through each branch is different. But then the total currents add up to the sum of the current that left the, the voltage device, the battery, whatever it was. As the number of parallel branches is increased, that overall resistance of the circuit drops or decreases. And then if you break one of the paths, so all of a sudden I remove one, it still flows current, just it goes through only the other paths. So again, it's like going down the highway and all of a sudden one of the lanes is blocked because of an accident. You can still flow, have traffic flow in the other lanes. It's just now there's more resistance, so the traffic doesn't flow as easily, right? So if it's a 3-lane road and all of a sudden one lane's closed, the other 2 lanes are flowing, it's just they've slowed down a bit. So now, when 2 identical lamps are in a circuit and are connected in parallel, the total resistance is less than the resistance of either lamp, the same as the resistance of each lamp, less than the resistance of each lamp, or none of the above. Okay? And the correct one is it's less than the resistance of either lamp, because again, if it was a 10 and a 10, 1 over 10 plus 1 over 10, that would be 2 over 10, which is 5. That's less than the resistance of either lamp. But it's not necessarily each individual one we're looking at. We're looking at the whole system. Any of them, it's going to be less than any of them that's in the circuit. So now if we consider a lamp powered by the battery, the charge flows out of the battery and into the lamp from the negative terminal to the positive terminal with a slight time delay after you close the switch, or through both the battery and the lamp. And it actually flows through both because it actually chemically has to, in that battery reactor, there's a flow in the battery of the current, of the electrons.